Let's solve one more example. And that's a pretty standard question found in all the textbooks. So here is my version of it. Let's say that I have a spherical block and there is no friction on it. Let's say that the radius of this block is r. What I do is I actually put a small mass m at the very top point. This point is actually an equilibrium point, right? But it's not a stable point. Even if a small push around this point will cause this mass to slide down. Right? So let's say we give it such a very infinitesimal, very small push, and it starts sliding down. It will slide down. Will it slide and remain on the track all the way down to the floor? No, it will actually split off the track. It will go away from the track. It will actually start flying. So the question is, at which point does the mass leave the block? Maybe a more entertaining way to ask this question is to frame the mass as a small child going off some slide and then asking when he'll actually leave the slide, okay? Now, how do we solve this question? Yes?
The slide off the track, the contact force and normal force is going to be equal to 0.
Exactly like the previous example we've actually solved. What does the normal force actually do in this case? The normal force does make sure that we actually follow the track. If there was no normal force, you can actually go below the track or you can go above the track. So normal force is just making sure that you fall with the same rate that this track is falling down. So we should equate the normal force to 0. So basically, the condition we would like to solve for is at this point, normal force is 0. Right? So our aim should be to calculate the normal force at any point for any angle theta and then set that normal force to 0. Okay? Is that point clear? This is the second example we're solving and by equating normal force to 0. All right. So let me ask you the following. If I start from theta equals 0 and I go an angle theta on this circle, what would be my velocity? How would I find that? Are there any non-conservative forces at play? No. Which means energy should be conserved. Good. So let's find out the initial energy. Is there any initial kinetic energy? No, the small infinitesimal push doesn't count. That's very, very small, right? So there is no initial kinetic energy. Let me choose the center of the sphere as my reference level. So what's my potential energy? M times G times R. How about energy at an angle theta? My kinetic energy will be 1/2 m, let me call this v theta square. And that's what I would like to actually find out, what this v theta is. How about my potential energy now? Potential energy is basically my height from the reference level. If that angle is theta, the angle here is theta. This is radius r. So this height is r cosine theta. So it's going to be mg r cosine theta. Let's equate these two. Mg r is equal to 1/2 m v theta square plus mg r cosine theta. M's cancel. So g r 1 minus cosine theta times 2 square root is b theta. We found the velocity at any point when I'm still on the sphere. But that was not what I was intending to find. I was intending to find the normal force, right? Good. So let's focus on that point. I'm making an angle theta, and my velocity is obviously like this v theta. Do I have an acceleration if I'm going with speed v theta on the circle? I obviously have a centripetal acceleration, right? So I have a centripetal acceleration. What's the amount of this acceleration? It's going to be v theta square over r. This acceleration must be caused by some forces. What are the forces acting on my mass? I only have two forces. One force is mg, which is making an angle theta. The other force is the normal force, right? And normal force is always perpendicular to the plane. So now, what is MA equal to? MA is equal to the sum of forces in that direction, right? So it's going to have mg cosine theta minus n. In other words, n apparently is mg cosine theta minus ma. That was what I wanted to find out. Now, n is mg cosine theta minus m v theta square over r. And v theta square, I'll just plug in the value here. N is mg cosine theta minus m over r, 2 g r 1 minus cosine theta. And at the critical point, this normal force is going to be 0. Okay, m just goes away, g goes away, r goes away, cosine theta minus 2 plus 2 cosine theta is 0. 3 cosine theta is 2. The critical angle is cosine inverse, arc cosine of 2/3. Yes? Yes?
I don't think that we should call a centripetal age as an age. We should, because there is also another age.
Yes, there is a tangential acceleration. Okay? That tangential acceleration basically tells me that I am not moving with constant velocity. It's telling me that I'm accelerating in this angular direction as well as I have acceleration in the centripetal direction. Okay, so I am still, nonetheless, whatever I call this, that centripetal part of acceleration, not the tangential part, but the centripetal part, is v theta square over r. Okay, you are right that there is another component, tangential component, which will be given by mg sine theta divided by m, which is g sine theta. Okay. So if I was cruel enough, I would, ask this question in the exam and ask you not the critical angle, but I would ask you where on the floor would that object land. Okay, that would just be mindless calculation. Now you have to do a projectile motion analysis for the rest of the. And sometimes people get cruel. So okay. Let's solve another example. Now that we're talking about toys today, let's talk about another toy. So there is this really simple toy, which is just basically two masses, equal masses, which are attached to each other by a spring of spring constant K. So, and let's say that the relaxed length of that spring is L0. Okay. So here's how the toy works. You basically compress it, and then you let go. Okay, you just pull your finger from it, and then this toy basically jumps off the ground, right? Which is always fun for small kids, for especially toddlers. Now the question is, obviously, if you just give it a small push and leave it, it's not going to jump off the ground. All right? So what should the minimum compression be so that lower mass leaves the ground? Did everyone understand the question? I have two masses tied by a spring. I'm pushing on the upper mass and then letting go. If it's a small compression, then the upper mass will just oscillate. But if it's a large compression, it's actually going to take the lower mass of the ground too. Question? Okay. We have gravity, we have the masses, and we know the spring constant. First of all, why should the lower mass even leave the ground? What is the equation I can use to gauge whether the lower mass leaves the ground or not? Yes?
The spring's pull must be higher than the gravitation.
The weight.
Yeah.
So you're basically saying that the spring should be stretched so much that it's actually pulling the lower mass with more than mg. You're right. Let me put it another way. What's the normal force the ground is applying on the lower mass? If the mass is not moving, it's exactly the difference between these two forces. The pull of the spring minus mg is countered by the normal force of the ground, right? So let's think about that. So I'll take as my initial point the following. I have a lot of compression. Okay. So this is compressed by delta. Okay. What are the forces on the lower mass looking right now? Here I have mg of the mass. There is also the F spring, right? And both of them are countered by a normal force. Now I let the upper mass go. The upper mass extends the spring. So basically here the spring is compressed. But when I let the system go, the upper mass actually stretches the spring, right? Now what are the forces on the lower mass? There is mg, but force of the spring is up, and normal force is again up. So if n is equal to 0, lower mass leaves the floor. All right? If n is equal to 0, then it means force of the spring must equal exactly mg. Can you tell me what will this delta final be if Fs is equal to mg? Fs is k times delta final, right? What's the spring force? K times the stretching or compression. So k times delta final must equal mg, which tells me that the final stretching of the spring to be able to move this object up must be mg divided by k. If my spring at any moment gets stretched more than that delta final, it will actually move the lower mass from the ground. Good. Now here is the thing. So this is my initial point. This is my critical point. I'm looking for the minimum amount of compression that's going to move the lower mass. What does that mean? It means I'm actually looking for the compression which is barely going to move the lower mass. So what should be the velocity of the upper mass exactly at this point? 0, right? For the critical case. If I actually compress more, it will have some velocity and it will pull the lower mass up. So at the critical point, velocity is 0. In the initial point, my velocity was again 0. Now the question is, are there any non-conservative forces at play here? No. So energy should be conserved. Can you tell me what's the initial energy? That is correct. I have the spring potential energy. So let me call this delta initial. What else? Potential energy. So here's something I'll do. I'll actually choose my reference level at the relaxed length of the spring. I can choose my reference level anywhere I want, right? Then, what is my potential energy in the initial situation? No. Is it mg times delta E or minus mg times delta E? It's minus. I am below the reference level. So it's going to be minus mg times delta E.
Isn't there potential energy for the lower
Maybe I should put that. You're right. So it should be minus mg times L0. But I'm really not interested that much because when I'm writing the final energy, there is no kinetic energy. I'll have 1/2 k delta final square plus mg delta final minus mg L0 for the lower mass. Because it hasn't moved, I will just cancel both. So what does that tell me? It tells me that 1/2 k delta initial squared minus mg delta initial is equal to 1/2 k delta final squared plus mg delta final. Okay? Okay, tell me why.
This is relaxed spring, right?
Yes.
So it shouldn't have
No. Initial situation I'm considering is not at the relaxed length. I am actually pushing it down and then letting the system go.
Okay, that's elastic potential energy.
Is 1/2 k delta initial squared. Then I have the gravitational potential energy. Gravitational potential energy is measured with respect to a reference level, and I can choose the reference level as any level I want, right? So I'm choosing it to be at the relaxed length of the spring, which means both of my masses are below that reference level. So I have minus mg delta E for the initial. Okay, good. Great. I already know what the value of delta F is. Let's write everything down. 1/2 k delta I squared minus mg delta I is 1/2 k mg squared divided by k squared plus mg squared divided by k. So on the right hand side I have 3/2 mg squared divided by k. Let's play around a little bit. I have 1/2 delta I squared minus mg over k delta I equals 3/2 mg divided by k squared, or delta I squared minus 2 mg over k delta I plus, no, minus, right, 3 mg over k squared is equal to 0. What do I do? Sorry? I had 3f. I multiplied the equation by 2 overall.
No, 3/2 mg squared over k, not 3/2 mg k, the whole thing.
3/2 is okay. Mg squared over k is okay. Then I divide everything by k, so mg over k squared. Right? So now I need the quadratic formula. Delta I would be minus b over 2a. So it's going to be mg over k plus minus 1 over 2a square root of b squared 4 mg over k squared minus 4ac 4 times 3 times mg over k squared, right? So this is going to give me 16 mg over k squared mg over k plus minus 1/2 4 mg over k to which root should I take? The positive one, right? Delta I, it must be a compression the way I defined it. So choose the positive root. my initial compression must be exactly 3 mg over K. Yes.
Why is delta I positive? I mean, if delta is positive, delta F should be negative.
No, delta I is defined as compression. That's why it should be positive.
Okay,
Right.
in that case, shouldn't delta F be negative?
No, delta F, the way I wrote things, is defined to as positive, right? Look at how I actually, that's a good question. I mean, I am writing, although I may be wrong, I'm writing everything consistently with the figures I've drawn. All right? So at the end of the day, if I find a negative result, it must be with respect to my figure. In my figure, positive delta I means compression, and positive delta F means stretching. Okay?
We did calculate the extension. Force by the spring is equals to Kx,
Yes.
and then mg is equals to Kx, right?
Yes, that's what we did. That's how we calculated delta F.
Why did we do the other one?
Okay, so the question, initial question was, how much should I actually compress this toy at the start so that when I let go, it's going to jump off the table. Okay, so that delta F is basically the stretching at the critical point. So we want to relate that critical point to initial compression. That's why we did the calculation. Question?
Are we taking the lower body and the upper body as separate?
Of course, yes, always. I mean, these two objects move separately. That's why I need to be able to apply F equals ma separately to them. Okay. Let's check. Did I reach my goal? Yes. How about units? What should be the unit of delta E? Delta I? Should be meters. mg is kilogram meter per second square. K. What was the unit for K? Spring constant. F is K times X, so it's going to be newtons per meter. Newton is F equals ma, it's kilogram meter per second square. So unit-wise, it makes sense. Does the result make sense? Do you think if I have a very weak spring, should I need to compress more or less? I would expect more compression. Or if I have a very tight spring, then a small compression would actually mean a lot of forces. So I think as a limit, K goes to 0, delta I goes to infinity is a good limit. Similarly, if these objects are very massive, I would need a lot of compression so that they jump off the table. So m going to infinity, delta I going to infinity does check. So I think it more or less seems like the correct result. Of course, I could have made some calculational error on the way, and it's not going to be 3, but it may be 5. Your unit check and limit check will not be able to tell you that number. Okay? So you have to be careful. Okay. Any other questions? No? I will solve yet one more example. Okay? Now, well, let me. So I have a pendulum with mass m. And I let it go. And the rope snaps. Should I say breaks? When it is exactly vertical. Okay. And I'll say this distance is h. How far away from the initial x does the object fall? So I'm leaving this pendulum. It swings quarter of a period. Okay. Then the rope snaps. Then I'll have projectile motion. I basically would like to find out what this distance is. And I'm given g. What do I need to do? I need to basically solve this problem in two parts, right? In the first part, I'll have this circular motion, okay? But that's accelerated circular motion. For example, if I asked you to find how much time it would take for this mass to complete quarter of the circle, you would not be able to find it. But even though we cannot solve F equals ma during this motion, it's basically a technical difficulty. You don't know enough mathematics to solve it. Okay. We can still know the velocity at the bottom. Why? Because we have this nice conserved quantity called the energy, right? So let's find this V first. So the strategy is to find V first and then analyze the second part of the motion. Is energy conserved throughout this motion? Yes. So it must be conserved in the first part, all right? So what is my initial energy? Let me solve this with another color. My initial energy is I have no kinetic energy, and let me choose my reference level to be really floor. So it's going to be mg times h, right? What's the, let me call this E bottom. What's my potential energy when the rope has completed the quarter of the circle? mg h minus r. And then I'll have 1/2 mv square. So let's equate my initial energy to the energy at the bottom. Initial energy was mgh. Energy at the bottom of the pendulum was mgh minus r plus 1/2 mv square. M's cancelled. H cancelled. Gr is equal to 1/2 v square, or v is equal to square root of gr times 2. So the first part of the motion, I actually obtained what I needed to obtain. Now I will analyze the second part of the motion. The rope has snapped now. There is no rope there. So this is just going to be projectile motion. Is energy conserved in the second part of the motion? Yes. But would that help me calculate the range of the throw? No. What do I need to do now? I need to actually use my dynamical or my kinematic equations to find out the trajectory of the particle after this point, right? And I know that in the second part, this is just going to be projectile motion. And in my projectile motion, my x coordinate was just motion with constant velocity, constant speed. So it's going to be my initial position plus v times t. How about my position in the y-axis? I'll have y at time t equals to 0 plus, if I have some vy, I'll have t minus 1/2 g t square, right? Because I'm saying this is my y-axis and this is my x-axis now. What's my velocity at, in the y direction at 0 time? It's 0 because I'm basically the rope snaps when the rope is vertical, which means my velocity is exactly horizontal. How about my position at that time, my y position? It's going to be h minus r. My x position will be 0. V I already know. So x of t is apparently just 2gr times t. Y of t is h minus r minus 1/2 gt square. Can I find the time of flight? What equation determines the time of flight? No. Tell me, what is the condition? The condition is that y of t at time of flight should be 0, right? I should hit the floor. My y, when I'm hitting the floor, my y at time of flight is actually equal to 0. So y at time of flight, which is h minus r minus 1/2 g time of flight square is equal to 0. So time of flight is apparently 2/g h minus r square root. So basically, what I should do is my length, the length I traveled in the x direction is 2gr times square root of 2g h minus r L. 2 goes out, and here's the interesting thing. G goes away. I have r times h minus r, which is somewhat counterintuitive. It tells me that if I actually even did the experiment on Mars or the moon, the length that's going to end up, this small mass is going to travel the same distance in the x direction. And why is that? Because this velocity is actually supplied by g. In the initial part, what does gravity do? It actually accelerates your object. It gives you the x component of your velocity. But let's first make sure that we actually reached our goal, which we did, right? H, r were given. So we expressed L in terms of this. How about units? Well, square root of meter square is meter, so no problems there. Here are some interesting limits though. What would happen if h is less than r? Then the question does not make sense at all, does it? If h is less than r, you will never complete the circle. You'll hit the ground before that. So what happens to my L in that case? L in that case would be square root of a negative number. It will be an imaginary number, which is great that my equations are telling me, they are shouting me that something went really wrong here. And that's a good thing, okay? What happens if h is exactly equal to r? You will just, hit the floor exactly at 0. H is equal to r, your L should be 0. And that also checks. My equations tell me that. So I most probably, well, I am not sure about this factor of 2. Maybe it may be 3. If I missed a factor, it may be 5. I don't know, right? If I was not careful enough. But I found the correct result, at least dimensionally correct result. And it also checks in those limits really nicely. Okay. Good. Any other questions? Nope. Then I'll see you in 2 days, 3 days.